Hello, we are going to be looking at rational functions and their end behavior for our next unit. So rational functions, when you see rational, think ratio, which is the same as a fraction. So we're dealing with all these functions that can be fractions, meaning there's something on the numerator and something on the denominator. And of course, with denominators and fractions, you can't divide by 0, so it says here, that's why the bottom d of x can't equal 0. Right? We have problems that happen at the situations. Right? And we end up getting, when we're dividing by 0 or dividing a lot of polynomials by themselves, right, we end up getting a lot of what's called asymptotes. Right? So we can just draw some here on Desmos. Let's say x squared. Oops, x to the second 6. There we go. And let's say plus 3x minus 2. And divided by, let's say, x minus 1. Right, you can see how there's like an invisible diagonal line, forget that right now, but there's like a visible diagonal line that this will never approach. So our questions for today is, how can we figure out what this behavior will do without having to actually use Desmos or a graphing calculator? Right? It's good to use the tools to see what's happening, but then at the end we want to not use them and be able to predict it anyway. Right? And you'll notice that if we change the degrees of the top and bottom, we have different outcomes. If I have the degrees that are the same, right, now it's not diagonal anymore. Or if I make the bottom bigger than the top, right, we have slightly different behavior. So how can we predict what happens without using a graphing calculator or Desmos? Right? That's our goal. So what we're going to try to do is predict what are these asymptotes, meaning the value of the graph that it gets very close to but never actually equals. Like for this one, we can see if we zoom out, right, the y values, let's see here, that get really, really close to 0 but never actually equal it. So the asymptote here is this purple line, y equals 0. We don't really care about what happens right here towards the graph. It's when we zoom out and go far left and far right, what does the graph do? What number does it get close to? Okay, so there's a way to predict this, and you can play around with this and just put in some different values. You can see anytime the bottom exponent, right, tends to be bigger than the top, it always approaches this line y equals 0. Okay, that just seems to be the case, and we'll find out why that happens throughout this unit. So that's the first case here, is that if the degree at the numerator, and let's say I did y, let's use f of x, and I'm going to make up a new one, let's say like x minus 2 over x squared minus 9. Right, the degree on the top is just 1, right? That's the leading coefficient. And the degree on the bottom is 2. So anytime you have this where the bigger exponent is on the bottom, you're going to get that y equals 0 horizontal asymptote. Okay? And it really comes from, let's look at y. If we were to ignore this part, because if we're doing really, really, really large numbers, and let's say x was 1,000,000, well, 1,000,000 minus 2 is still a really large number. So we kind of ignore anything after the leading coefficient because it really doesn't change the answer so much. Same thing here. If I have 1,000,000 squared compared to 1,000,000 squared minus 9, well, the minus 9 really doesn't affect that overall answer. So we're really looking at what's 1,000,000 divided by 1,000,000 squared, right? Something like this, right? Divided by 1,000,000, and I could say 1,000,000,000, but squared. Obviously, this bottom number is going to be a lot bigger, and when the bottom number is bigger than the top number, it basically equals 0, right? It gets closer and closer to 0. A small number divided by a huge number is going to be 0, and that's why we get that horizontal asymptote at 0, because the bottom is just so much bigger than the top. Okay. So that's the way we want to look at and understand why these graphs behave the way they do. Okay? So let's look at another one. Let's say f of x equals, let's say, 8x squared minus 1, all divided by 2x squared. Right? Squared. plus x minus 3. So once again, if we just don't really pay attention to this part on each of these functions and think about what's happening here, well, any value of x, like 8 times a million squared divided by 2 times a million squared, it's almost like the million squareds, or whatever large number or super small number we plug in, will just cancel out with one another, right? These x squareds just cancel out, and we're left with 8 over 2, right, which just equals 4. So in this case, we end up with a horizontal asymptote that is just the leading coefficients, or the ratio of the leading coefficients. So it looks something like this. Go over here, and I graph that. Number 2, yep. And you can see that if I change this to 4, yeah, on both sides of the graph, if I zoom out, right, it just gets closer and closer to positive 4. This line just gets closer and closer, 3.944, and even if I zoomed out to some really large number like a million, it'd still be just really close to it, but never actually equaling it. And it's the same behavior, of course, on the other side. So it's not just at positive infinity, it's also as we go to negative infinity, same thing is happening. It's just coming from the other side. This time it's 4.04, and getting slightly smaller and smaller the more we go to negative infinity. And so that's when the coefficients are the horizontal asymptote when the degrees are the same. Okay. And then we have the other case when the degree of the numerator is larger than the degree of the denominator. So we can look at another function. Let's say x squared minus 5x plus 4 over x minus 2. So in this case, we have a 2, right? And the degree of the numerator is bigger than the degree of the denominator, right? I can show this here. Here, number 3. There we go. That's number 2. Let's go to number 3. There we go. So when the top degree is bigger than the bottom degree, you see we get this slant, right? So we don't have a horizontal asymptote, right? We no longer have some line that approaches from both sides, right? It's on a diagonal. On here, we're going to say has no. Right? But it does have this slant, right? So the question is, how can we figure out the equation of the line that this follows, right? How can we do that? And we're going to do it by actually rewriting this polynomial using some long division. I'm going to go back over here. I'm actually going to divide x minus 2. I'm going to divide that in to the numerator. X squared minus 5x plus 4. All right, let me zoom in on this. There we go. Plus 4, and let's do the long division. All right, so if you might remember, we want to see how many times does x go into the leading term, or x times what gives us x squared. So we're going to say x. X times x is x squared. And x times negative 2 is negative 2x. And we need to subtract. Right, now we need to subtract all of this, right? So really subtracting x squared. We're also subtracting negative 2x. So x squared minus x squared, that's 0. That's what we wanted. Negative 5x minus a negative 2x, right, is going to give us negative 3x. And then we repeat the process. So x times what equals negative 3x, and we come up with negative 3. So negative 3 times x is negative 3. Oh, I forgot to bring down to 4. Bring down to 4. Now we can multiply. Negative 3 times x is negative 3x. And negative 3 times negative 2 is positive 6. Do my subtraction. So negative 3 minus negative 3 is 0. Good. 4 minus 6 gives us negative 2. That's our remainder. Okay, so technically, our answer is x minus 3 plus a negative 2 over x minus 2. Now this part's not so important, but this right here, that's actually the equation of our asymptote. If I go back to here, and I show you that, let's take off the horizontal, you can see both directions it approaches that line. So we just have to do a little long division to find out what the slant asymptote is by doing long division. We could even rewrite our function using our answer, which was x minus 3, the diagonal asymptote, and then with our remainder, which was negative 2 over the original divisor, x minus 2. Right? And you can see that these two are the same graph, the one we started with, right? And then our quotient here, x minus 3 plus the remainder, and it's the exact same graph. Right? So this x minus 3 without that, I'll take this off, right? That just gives us that diagonal asymptote. With the remainder, it gives us the actual graph. Yeah, gives me the actual graph. And if I varied this, just for fun, let's see here. Yeah. Guessing if I do this, and we look at it, the more the remainder that I add to the graph, right here, the closer it gets to that actual slant asymptote. Now this is not something you have to do, it's just interesting behavior to see how things work. You just need to be able to get the equation of this line and know when to do the long division in order to find out this. So we want to know, just by looking at this, well, the top degree is bigger than the bottom degree, therefore I have to do the long division, and then my answer will give me that diagonal asymptote, or that slant asymptote. Okay, so let's practice that just a little bit more. This is a skill from Algebra 2, but we haven't maybe done it in a while, so we just want to make sure we still remember it. So let's zoom out. Yeah, let's go back here. It said find the horizontal asymptotes for the given functions and provide a reason. So first we have a degree of 0, right? Since there is no x value, this is like an x to the 0, which equals 1, right? So we have a 0 on top and a 2 on the bottom. So since the 0 is less than 2, using your notes on the other page, what is the correct asymptote? Does it have a horizontal asymptote? Yes or no, and why? You go back here. When the numerator is less than the denominator, we go back to our notes. Degree of numerator is less than the denominator, then we should have a y equals 0 horizontal asymptote. So here, we say y equals 0. Right? And our reason or justification is right here. That's our justification. It's because 0 is less than 2. And we know that these are the degrees. We go on to B, same idea. We can look at these and say, right, those are the degrees. So since they are the same, therefore, what was the rule? You go back to your notes. When they are the same, you take the ratio of the coefficients, right? Because it's like they just cancel out. We go back here. So remember, large numbers, the negative 3 won't really do anything, either will the positive 3. And then these x's also cancel out, so you're just left with 3 over 1, which is 3. So therefore, our horizontal asymptote will be at 3. And lastly, the degree of the top, 2, is greater than the degree of the bottom, which is 1. Therefore, and it's asking, find the horizontal asymptote, right? And therefore, this does not have one. So I'm going to say no horizontal horizontal asymptote. We've got to practice spelling this correctly. A-S-Y-M-P-T-O-T-E. Make sure we spell that correctly. And we know from the last example we did that this has a slant or diagonal asymptote. So that's the next step. Let's just practice doing that. So we have to do some long division, all right, which is okay. This is something very doable. So I'll write it out. Dividing x squared, the bottom, minus 2x plus 2 into the numerator. So give yourself some space. Do this in an organized fashion. I find the people that miss this, when this is missed, it's usually how good your writing is or how much space you give yourself. Right? In other words, the way to miss this is write sloppy and try to squeeze it in a small space. If you ever need more space to do the work, feel free to do it on another piece of paper if what you have is not big enough. So we just have to go through this process. So x squared times what gives us 2x to the third. Right, so that'd be 2x. Right, it's going to be this times this has to equal this. So I'm just working backwards. So 2x times x squared equals 2x to the third. 2 times negative 4x, negative 2x is negative 4x squared. And 2 times 2x is just 4x positive. There we go. Now we have to subtract all of these. So this minus this, of course, is 0, what we wanted. 3 minus negative 4, that's going to be 3 plus 4. So we got 7x squared. And we have negative 4 minus 4, which is going to be negative 8. And then we can bring down this 1. Now pause it to see if you can do the next step on your own and then check. All right, let's keep going. So x squared times what is 7x squared? That'd be 7. So 7x squared. Multiply these two. 7 minus 2x minus 14x. And 7 times 2 is just 14. Subtraction. That's what we're doing. So we get 0. We get negative 8 minus negative 14, which is negative 8 plus 14, 6x. And we get 1 minus 14, which is negative 13. And as soon as this degree is bigger than what we have here, we know that we have finished. Okay, so we don't need to go any further. This is the remainder. But our answer is really just this right here. And go ahead and check this in decimals. You saw me do it. Type in the original function, and then you can type in 2x plus 7, and you can see that this function approaches this diagonal in both directions. Okay, try the next one on your own. See if you can do this by yourself completely, and then verify it in decimals. All right, you should have gotten 3x minus 1 as your slant asymptote. Again, make sure you could do this part on your own and check it. Right? You're not merely copying things down when you take notes. You should be practicing this so when you come to class to do the problems, you've already gotten somewhat of an introduction on practicing this, right? So make sure you are doing these practice problems on your own just to make sure you got it down. Right? You'll find out where you're missing mistakes on negatives and things like that, and you want to work all that out before you start doing a lot of these problems. All right, let's move to the back page here, and we're looking at the end behavior. So we're looking at end behavior, or really big or really small numbers as x goes to positive or negative infinity. That's the end behavior. Right? What's happened at the ends of the graph. Right, so when we're looking at this, as before, we're not really paying attention too much to anything but the leading coefficients of the top and bottom. Think of this as really, really large or really, really small numbers. what's going to happen there. Right? So we don't really need to think about this part of the graph. It's really what's going on here. Right? So, and if we look at this part only, the 2x to the fifth over x to the third, this in itself simplifies, right? Because x 3 goes into 5, we'll subtract, so we can cancel out 3 of these on the bottom with 3 on top. We'll be left with 3x squared, right? So the behavior is going to be simply the same behavior as this graph. Okay, so let's look and see what that looks like. So here's that function. Right? And remember, we're just kind of saying we don't really care about this. And pay attention to the end behavior. So if I look at this whole graph, like down the middle it's going way low, but as x gets really, really big, really it's up here where the graph just seems to keep going to the left and to the right. Okay, so we can zoom in a little bit on here. Let's get the x-axis a little tighter. Negative 10 to 10. There we go. Now we can see as we go up here, yeah, the left and right are just going to go up forever. And you can see this graph kind of resembles something we know. So let's keep that and let's look at without the ends of both functions. So let me just look at this part. X to the third. Right? And it has the same behavior. Right? And you might notice this also is the same as if I divide those. Let's see here, 2x to the second. And I think this is supposed to be a 2. That's why that came out different. There we go. Yeah. So from this, we can tell, just by ignoring this part and knowing this part, looking at this and reducing it, that it has the same exact behavior. If we look at the original graph, right here, this original graph has the same end behavior as just simplifying the leading coefficients and variables. Right? So that's pretty cool. So we can find out, well, if we know what the end behavior of a parabola was, or is, then we know what the end behavior of this is. So we can say, since we have 2x squared here, that the fancy way you write this is the limit on the left side, which is negative infinity. That approaches positive infinity. Right? The left side goes up, right? And the right side. Right? And we got positive infinity, right, equals positive infinity. Remember, the bottom here is left and right. Negative infinity means the left side of the graph. Positive infinity means the right side of the graph. And these both mean it goes up on both sides. So this is a fancy way of saying, while you're looking at the graph, yeah, both sides of this graph go up, the left side and the right side. It just has a lot of little baby steps we have to put in there. All right, so let's look at the next one. Go down. There we go. All right, so see if you can figure out what this is. All right, what does this simplify to? Notice how the degrees are not in descending order, so we're not going to have we don't want to make a mistake that, oh, let's just take these two, whatever's in front, and ignore this, because he just scribbled out on the ends. Well, the last ones, it was in descending order. So before we do that, we want to put the highest degree first. Now we can actually discard the lesser degrees. Okay. And look at this. So we'll have negative 5x to the third. Right? And we should know the general behavior of this, right? That was 1.6. So this is a cubic, right? So it has some general shape like this. But since it's a negative, we know it has a general shape like this. We don't really care what's happening in the middle here, right? It might have a lot of those mins and maxes, or maybe none of them all, right? It could just look like this. But the important part is that we know the behavior on the ends are identical. So as we go left, the graph goes up, and as we go right, the graph goes down. So the fancy way of writing this, as the graph goes left, right? And we can actually put this in here. Limit as this graph goes to the left, it's going to be positive infinity. And then on the right-hand side, meaning to positive infinity, of the same graph, negative 5x to the third, that goes down. There we go. And that's a proper way of documenting the end behavior for this without even having to graph it. Now, if you should go back and actually check on Desmos that this makes sense, and that's what it comes out to, so you can see it and then believe it even more. All right, and that'll do it for the beginning of this unit for horizontal and the slant asymptotes.